Okay, so in front of us we have a resistor circuit. We have an EMF of 42 volts, and that is connected to a circuit involving an 8 ohm resistor and a 4 ohm resistor set up in series, as you see here, and that in turn is in series with a parallel loop involving a 6 ohm resistor and a 3 ohm resistor. So instead of asking a specific question, what is the current through this resistor, what is the voltage drop across this resistor, let's just completely characterize the circuit. Let's just figure out everything we can figure out, or at least within reason, with this one circuit. So first step is to look at it and see if I can reduce this to an equivalent resistance. And I can. I don't have to get more complicated than that. You should see later that if you can't reduce it to an equivalent resistance, then there are some other tools that we can use to analyze the circuit. But in this case, there's only one EMF. There's no strange configuration, so I think I can just reduce this whole thing to an equivalent resistance and see what information I can get out of it. So I'm going to do this in the interest of time. I'm going to do two steps at once. I'm going to reduce this section to an equivalent resistance. We get a different color. And I'm going to reduce the loop to an equivalent resistance. So the section in red I'll do first. It is a series of resistors, 8 ohm and 4 ohms. And I know how resistors add together in series, or I know how resistances, I should say, add together in series. They just add together. So my equivalent resistance of my red circle here is just going to be equal to 8 plus 4. I'll factor out the units, which is just 12 ohms. Okay, no big deal. Let me do my blue section. So this is a parallel configuration, and I know how resistances in parallel add together. What I get is that the equivalent resistance, the inverse rather of the equivalent resistance, is equal to the sum of the inverses of the resistors that make up the loop. In this case, it's going to be 1 over 6 ohms plus 1 over 3 ohms. That's a terrible looking omega. So what I get out of that is 1 over 2 ohms, if I do that correctly. And 1 over 2 ohms is my, notice the ohms, the units are in the denominator. It's not 1 over 2 parentheses ohms, that's 1 over 2 ohms. So to take the inverse of that is pretty simple. So what I get is that the equivalent resistance of my blue section is just 2 ohms, 2 over 1, right? So now I can redraw my circuit. Let me go to a different page. I can redraw this. Here's my EMF, still 42 volts. Let me change colors on my pen back to black. Still 42 volts. Now my red section is going to yield one resistor and my blue section will yield another resistor. This was 12 ohms and I found this to be 2 ohms. So let's just compare these two for just a second. Let me go back to the original picture. What has happened here is the red loop, 8 ohms and 4 ohms in series configuration, has become this 12 ohm resistor. Now it's important to keep in mind that this is not the actual circuit. This is an equivalent circuit. In other words, if you're the battery, the current that is that you're producing, for lack of a better word, is the same in this circuit as it is in this circuit. That's what we mean when we say equivalent. From the perspective of the battery, nothing has changed between this circuit and this circuit. Okay, and of course the blue loop, my parallel of 6 and 3 ohms, has become this 2 ohm resistor. Now we can see what's going on. I just have another series configuration. I know how those equivalent resistances work. It's just 12 ohms plus 2 ohms for a total resistance of 14 ohms. So then I can redraw my circuit again if you feel the need to do that, which I typically do. That's again 42 volts. Nothing has changed with my EMF. I've got one, oh, sorry, I lost the iPad there. I've got one resistor here with a resistance of 14 ohms. So because I've lost a lot of space here, circuit problems aren't easy, but they do tend to take up a lot of real estate. Let me just go to a clean sheet. I'm going to redraw that my EMF, my 14 ohm resistor, my 42 volt EMF. There we go. Now I can start to answer questions, right? What if I want to know the current in each of my resistors? Well, I start answering that question by analyzing this particular circuit, which again is an equivalent circuit. It's not my actual circuit, so I'm not answering the actual question by looking at this circuit, but this gives me some tools to answer the actual question. So to analyze that, I just start with Ohm's law. V is equal to IR. I should point out that some textbooks will insist on saying delta V, and that's totally fine. I'm going to leave it off because I get tired of writing it. You will also find some textbooks that tell you that this is not Ohm's law, which is technically true, but it is derived pretty easily from Ohm's law, which has to do with conductivity and resistivity as opposed to current and resistors, but you can get here pretty easily. That's okay. So to find out the current here, I just solve for I, which is equal to V over R. In this case, that is 42 volts. Having trouble writing V's today. Over 14 ohms. And if I do the math correctly on that, I get that my current is 3 amps or 3 amperes, right? A volt divided by an ohm yields an ampere, or an amp for short. Alright, so that is the current through this resistor. Yay, what have I gained by that? I'm being asked for the current through each of the other resistors, right? Well, if you know how circuits work, and we do, you know that in a series configuration, the current through every resistor has to be the same, and that's because we don't give it anywhere else to go. We don't give it a junction. We don't give it a way to branch off and split itself. You just have one pipeline. No matter what you shove in that pipeline as far as resistors, you just have one pipeline, so you have one current flowing through that pipeline. So let's go back one step and look at this. So if I look at this configuration here, which is an equivalent configuration, what I get is that the current flowing through the 12 ohm resistor and the 2 ohm resistor has to be the same as the current flowing through this one, which is 3 amps. Right? But again, this is also an equivalent circuit. I haven't actually answered the question yet, so let's go back one more step. Let's go back here. Well, now I can say that the current flowing through the 8 ohm resistor and the current flowing through the 4 ohm resistor is 3 amps because there's nowhere else for it to go. Now that changes a little bit when I get to the junction leading to my parallel loop, but what I can say is that the total current flowing through that loop has got to equal to 3 amps. Okay, so let's go to a fresh page and see what that looks like. So in that case, I have a loop which splits like this. I've got 2 different resistors, but I know that there's a current coming in. Let me change to another color. We'll go with yellow for current. The current is coming in, but at this junction, I know that the current is going to split. So I've got part of it going this way, and I've got part of it going this way. Well, all I'm saying with this analysis so far is that the current coming in here is 3 amps, and as it leaves, well, all the current that's split at this first junction has to come back together at the second junction. So the current that ends up leaving the loop is also 3 amps, right? So if I add up the current flowing in this leg and the current flowing in this leg, I'm going to have to get 3 amps. I don't have any other sources of current in there. Conservation of charge is a thing, so I'm going to have to get 3 amps, right? So let's see what I've said so far. The current flowing through the 8 ohm resistor, we'll call that I1, is equal to 3 amps. The current flowing through the 4 ohm resistor, we'll call that I2, is equal to 3 amps. We'll call this I3 and I4, right? And I would really like to know how much current is flowing through I3 and I4. So I'm going to figure that out next. I'm going to have to stop this video because I'm reaching the end of time, and we'll pick up in a new video.